we've been looking at this idea of quadratic equations, okay? And like you've seen, we can graph them, we can find certain features about them, right? But the power of quadratic equations, and like these questions keep coming up, you know, why are we learning this? What's the point of this, right? I'd hope that when we learn about these quadratic equations, they're interesting enough that, you know, we can just learn them for the sake of them, right? There doesn't have to necessarily be a reason for it. But more often than not, these mathematical concepts, there is an underlying purpose or an application of them. And quadratic equations in particular have that. Let me give you this question here. So imagine you've got a piece of wire, right? I've got an HDMI cable. And you bent it so that it was the shape of a rectangle. It's bent into the shape of a rectangle, okay? My question is this. If it's bent into the shape of a rectangle, what's the largest area it could be? Okay, some of you might have seen this before. So have a think about it, right? If I take a piece of wire, right, maybe it's a, I don't know, paper clip, or maybe it's a pipe cleaner or something, right? Here's one rectangle that I could do, right? How do I kind of change this though? What happens? Because I have a fixed length that I can work with. I'm saying I've got 30 centimeters. Right, how can I change it? Can someone give me an example of a rectangle that I can change it to be? Yeah.
Having the longer height?
Yeah, I could, I don't know, do it like that maybe. And it's a bit hard with an HDMI cable because it's so curvy, right? But, I don't know. I think you guys might get the idea, yeah, if I can try and block this out, right? So I could create a rectangle that looks like this. I can create a rectangle that looks like this. Okay, so I can create all different shapes and sizes. I can even create a really, really thin one, right? Because I've got a fixed length. It doesn't say anything about the rectangle. I could make a really, really thin one, like super thin like that. You notice though, even though they're the same fixed length, what do you notice about these areas? They're going to be different, right? So here's the thing, just because I have the same perimeter, right? Because this is what the piece of wire, that's going to be the total length around, right? That's going to be my perimeter, right? I can actually have different areas. The question is, what's the largest area it could be? Another way you could say it is, what is the maximum? Hey, hang on a minute, what have we just been learning about? Quadratic equations, we can find their maximum or minimum. And this problem relates to a whole kind of family of problems called optimization. Right? It's talking about what's the most efficient way, what's the minimum cost I can have, or the maximum area that I can have, right? So let's think about this. In order to attack an optimization problem, you can see they haven't really given you much to work with. They've given you some information. You've got a piece of wire, and you know it has to be a rectangle, right? Like, okay, what do I do next? What you want to do is you want to think, all right, what kind of information do you have, and how can you relate it to your diagram? So let's say these side lengths are x and y, right? How can I relate the piece of wire, right, the information I have, to these variables here? How could I relate them? Sorry, yeah? xy equals to 30. Would we agree?
The wire is long. No, that's the area.
Okay, so what has Matt found here? He's found the area. So if you multiply these two side lengths, we get the area of a shape. We know that. But in fact, the area is not 30. Yeah, so what does 30 represent? 30 represents the perimeter. Right, okay. So I can still keep this equation. That's okay. I'll keep it. Right, but it just represents something different. It represents the area. Okay. But I know that 30 is the perimeter. Is there another way I can write the perimeter with these variables here? Yeah, think back to what these rectangles, the side lengths, opposite side lengths are the same. So x plus x and y plus y. If I add them all together, I get the perimeter, right? So 2x plus 2y is equal to 30. I'm still in a little bit of a pickle though, right? Because it doesn't seem like, hang on, I've got a equals to xy, 2x plus 2y equals 30. What can I do with these? Right, the goal of this, if you're thinking back to this idea of quadratic equations, your quadratic equations are usually in the form y equals to something. And on the other side, you have your equation in terms of x. So what you want to do now is you want to think, how can I get an equation only in terms of x at the moment, right? And right now, I kind of have both of these. But what you notice is you have two equations. You have this one, and you have this one. And you've worked with kind of simultaneous equations before, right? My suggestion to you is that we have an equation in terms of x. If I can find an equation in terms of x, then I can see what this graph looks like, okay? So how could I do that? Well, let's look at this one here. Let's simplify this a bit more. What's something I could do with this one over here? Sorry? Yeah, you just divide both sides by 2, right? Yeah, let's focus. X plus y equals to 15. Jot that down for me. X plus y equals to 15. Now, if I think about it like this, right? I said I want an equation in terms of x. If I want an equation in terms of x, let's go back to this area equation that I have here. What do I kind of want to get rid of? If I just want an equation in terms of x. If I just want an equation in terms of x for this one, for this area, right? What do I need to get rid of here? I've got this y variable, right? How can I get rid of it? Or how can I rewrite in a different way that only involves x? Yeah, right. You go to this equation that you have two equations here, right? And if your goal is to write something in terms of x, then you say, hang on, if I write y in terms of x, or y equals to 15 minus x, right? If that's an equation that I can use, what can I do with that? I can I'll sub 1 into a equals to xy. And what will you get? You'll get, yeah, so remember, what does xy mean? It means multiplication. So I'm taking y, which I can find here. I can rewrite it as 15 minus x. This looks interesting now. What does this look like to you? A quadratic equation. How do I know it's quadratic? Because if you expand this out, remember, quadratic, we say they have to have powers of 2, right? So if I expand it out, I'll get 15x minus x squared. What can you tell me about this parabola? It's concave down. Should be next there. It's concave down, yeah? Anything else? Yeah? What makes you think that? Actually, this should be a as well here, actually. X. Okay. I want to draw this out, but I want to explain what this actually means. We have two different forms here, right? This is our quadratic. Quadratic, and we know it's concave down because the coefficient of x squared is negative. Okay, but this form is powerful. Why is this form good? Because this form here tells you very easily what your intercepts are going to be. Right? If you let this side be equal to 0, either x equals to 0, or what's the other possibility? 15. Okay, either x equals to 0, x equals to 15. So I have 0, and I have 15 here. And as you guys mentioned earlier, it's concave down, right? So it looks like this. Can you think about now, what does this parabola represent? Because right now all I've done is I've said, all right, here's a question, here are some equations we can create. What does this parabola actually represent? How did I get a parabola when I was talking about rectangles and y's? Yeah, what does that represent? So this is a maximum. We know that from our graphical features. But what does this represent?
When x is equal to one value, y equal to another, it tells you what's the area.
Yes, that's exactly what it is. Okay, think about y. Think about y, right? Say that again for me, Angus.
Well, if you have x equal to, let's say, 1, then use the quadratic formula, you can find out the y and you can find out the area.
Okay, let's actually test this out, right? Really simple example is this. If x is equal to 0, right, that means your rectangle kind of doesn't exist. That's why the area is equal to 0, okay? And if x is equal to 15, that means like both of these lengths are 15. And so like your rectangle doesn't have any area either. And anything in between that, we get, right, whatever the value of x is, right, that tells me, right, whatever this length is, this a value, right, this is actually going to tell me how much area I have inside here. Can you guys see that? Right? So this parabola is a representation of all the possible areas that you can get. Okay, can you write that down for me? This parabola is a representation of all the possible areas you can get, right? Because if you think about it, we have all these possible areas I can get. It's going to depend on what x and y actually are. So then we go back to the original question, right? We say, okay, well, my original question was, what's the largest area it could be? And I think you're starting to see now, right? The parabola is a powerful representation of this. Because if I want the largest area that can be, what point do I have to look at on my parabola? The maximum, right? How do I find the maximum parabola? You know how to do that now. There's a few ways you can do that. You can use your kind of halfway between the intercepts method. You can use x equals to minus b over 2a. Let's use that just to make sure it works. X is equal to minus b over 2a. That's going to be the axis of symmetry. And in this type of parabola, you have to be, let's rewrite it so we make sure we get these coefficients right. It's going to be negative 15, or negative 15 over 2 times negative 1. And what does that give you? 7.5, right? So what's this saying? This is saying, well, if x is equal to 7.5, if your width of your rectangle is 7.5, that's when you're going to get the largest area for your rectangle. What is that area, though? Let's find it. How would I find that?
Just sub 7.5 back into the quadratic
Yeah.
equation to get what y equals.
And this is why it's really important to understand what we're actually doing here, okay? There's a lot of concepts. First, you had to create an equation, firstly, and then we had to draw a parabola. But the important thing to realize is this. This value is going to give you what the area is going to be when x is equal to 7.5. I already established that this is a maximum, okay? So if I take 7.5 and I put it back into this equation, can you do that for me now and tell me what you get? Because that's going to tell me the largest area that this can be. Can you find that for me? 56.25. 56.25, wow, okay. So somehow we can create an area of 56.25. That's going to be the largest. How do we get that? Well, why don't we just see this in action, right? What if my x is going to be 7.5, what's my y value going to be? I can just put it back into here. And in fact, hang on, you'll notice 15 minus 7.5, that gives you y is also equal to 7.5. Hang on, so what kind of shape is this? This is a square. So the largest rectangle that we can create is a square. Wait, what? What's going on there? Why is that? I first started off with the problem. The problem was this. A piece of wire 30 centimeters long is bent into the shape of a rectangle. What's the largest area that it could be? Okay, and I created these equations here, and then I drew this parabola, and I found these lengths and widths. And it's telling me this, that the largest area that you can make out of this shape is when the x and y's are 7.5. If you're wondering why the answer is square, right, it's because, well, square is actually just a type of rectangle anyway. So it's kind of a little trick question there, right, for you. But if you think about it, right, a square will retain the most area. Because if you have a super thin rectangle like this, right, it's not going to have much area inside there. So you kind of want to make those lengths as spread out as possible in order to get that maximum area that you have, right? Okay. And you can try with a whole heap of different values. You can try like, if x is equal to 5, for example, then y would equal to 10. So that's one rectangle you could use. 10, 10, 5, 5. Those would add up to 30 if you add up all those values, right? 10, 10, 5, 5, yeah. What's the area of this shape is just going to be 50, right? And that's smaller than this one. And in fact, you will find that it's not possible to find an area larger than that using these measurements here. So that's how we can use quadratic equations to actually look at a kind of, problem and model it that way. And you've seen examples like this before, but this one's quite hard because you have to develop the equation yourself, and then you also have to take that equation and do some work to find out the maximum. Any questions about that? Awesome.